Right, so just quickly, in case people don't know what Deliveroo is, we are an on-demand food delivery company. We sit at the center of a three-way marketplace between the riders, the restaurants, and the customers. And so we partner with around 10,000, or sorry, tens of thousands of restaurants, quite a lot more than 10,000, across 13 markets. And we work with a fleet of tens of thousands of riders who form our delivery network to deliver these orders. Right, so here we have sort of the rough flow of our customer when they come to our site. So first, if you're a hungry customer who wants some food, they'll come to our site or app and order our food. And this is when my team, the logistics algorithms team, starts to get involved. And so from there, we have a machine learning algorithm that predicts how long the food's going to take to prepare. We also have algorithms to predict how long riders are going to take to travel. So we can assign riders to get to the restaurant exactly when the food should be ready. We then have algorithms to work out how long they're going to wait and how long they're going to take to deliver the food. And so Frank, our order assignment algorithm, takes the collection of all the orders that we've received and all of our riders and finds the optimal assignment between these such that all of the customers get their food warm and they're happy, like the lovely happy customer over here. And to give you a bit of an idea of the scale of this problem, this is a map from central London, just where we are. All of the Deliveroo logos on here, these match the app of riders who were online some weekend earlier in the year, I think in the summer sometime. And all of the orange knives and forks are the restaurants that we have on the platform. So this gives you a bit of an idea of the scale of the problem we're dealing with when we're trying to choose which rider should deliver which order. But so that's logistics. What about load management? What am I talking about there? So load, roughly speaking, is how we tell how many orders we have compared to riders, how our capacity to deliver orders, that is, how much rider time we have, compares to the number of hungry customers we have who want some food. And load management only really comes into effect when we have a lot more orders than we have riders, roughly speaking. Now, we have predictive algorithms that predict the order volume that we expect, day to day, hour to hour. And we have algorithms that work out how likely it is that riders are to attend, as well as a system for riders to request when they want to work. All of this means that we typically have the right number of riders on the road at any one time to deliver the orders that we receive. But sometimes things happen that means that the right number of riders aren't there. And so load management really only kicks in when something's gone wrong. One of the typical situations that we like to talk about when this happens is sort of bad weather. And in bad weather, we do things to try and get extra riders on the road, but at the end of the day, if it's snowing outside, riders don't really fancy going out and getting wet and cold, and so there's less riders that go out. Also, customers don't really want to go out to get food, and so we get more orders. And this sort of double whammy means that we no longer have enough supply to deliver to all the people who would like food. Another example other than weather would be something like events. Like if we haven't predicted an event's going to happen and everyone's watched the same football game, then they may all order at the same time, and suddenly we just get this wave of orders, which we can't then handle at that time. And so we have these algorithms in place to manage this. And our goal is to make sure that we don't have customers sat at home waiting for their food hungry, not being able to get their food. So to give an example of what this sort of looks like and what we do about this, here I have a graph at the start of the day where on the y-axis there we have the delivery network load. And so when it's low, we're nice and quiet. We've got a good number of riders to deliver the orders. And then as a customer, you're going to see a large number of restaurants. Here, 9 just for visualization. And as we start to get busy, we start to not be able to deliver the orders as quickly as we otherwise would. And so we start to reduce the number of restaurants you see. And as we get busier and busier, we reduce it further and further. Eventually, we stop showing restaurants altogether. This is so that every customer who orders from us has a good experience. And if the algorithms work correctly, then it should come back down again, and you'll be able to see all of your restaurants as you did at the beginning. But so on this graph, I just have this delivery network load. And what do I mean by that? How can you measure that? If we're going to have an algorithm that works on this, we need to quantify that somehow. And so when we first started working, I go back to this graph of orders versus riders. We took the ratio of the number of orders we had to the number of riders we had, and used that as sort of a way to inform some of our human operatives who would manually stop people from being able to order. And this worked in the early days, but as we've scaled up, this doesn't really scale with the company. And Just looking at the number of orders relative to the number of riders, you start to run into problems that not every order is the same. And so you can kind of see in this map. Here we have a rider at A, a restaurant at B, and 2 customers at C and D. Now, the cost to us in terms of the amount of time it's going to take a rider to deliver this order for C is going to be less than it is for D, just because they've got to travel further. And furthermore, in this example, this is where the rider's actually delivering both these orders. So we offer them the chance to deliver both of C and D from B at the same time. And this will reduce the per order cost to us in terms of rider time. And just that ratio of orders to riders doesn't take into account any of this information. It doesn't capture that. And so it becomes a kind of a bad proxy for how busy we are. So instead, if we said that they take different amounts of time and that causes us to be different amounts of busy, maybe we should look instead at the amount of time it's going to take. And before, I said we had this algorithm, Frank, that decides which riders we offer which orders. Frank actually looks right into the future for all the orders we have and all the riders we have, and decides roughly which orders we're likely to assign to or offer to which rider in the future. And as you can see here, with 3 example riders, they all have 2 orders, but they're going to take quite a different amount of time between them to deliver these 2 orders. That ratio is not the right measure here. In fact, maybe just time until the rider is free could be a better measure. So if these were all in a similar area, we could say that, well, the next time we're going to have a rider free is going to be in roughly 25 minutes. And this could be a better measure for how busy we are. But when we had this restaurant list, the customers had a large selection of restaurants they could choose from. And maybe they really fancy one specific restaurant. And maybe that restaurant is here. And the final customer on the previous chart could be where these 3 riders are now. And here we see that second rider, the motorbike, is actually much further away from this restaurant the customer wants to order from. And so instead, we can add that travel time onto when they're free, and thus get the time that the rider would arrive at the restaurant if they finished what we already had planned for them. And this is a much more realistic view of how busy we are in terms of a specific restaurant. And we do this. We, for every restaurant that is open, we look at how long it's going to take us to get riders there after they've completed their orders, and use this metric in order to determine how busy we are. And so here we would use 35 minutes. And just to show you that this sort of metric makes sense, I have some data from a few weeks ago. So on the x-axis here, we have that metric I was just describing, this amount of time it would take to get a rider to a restaurant. And on the y, we have a couple of measures for how busy we are or how degraded our service is. So on the left, we have delivery network delay. This is the amount of time or how delayed the rider is going to be arriving at the restaurant. And we can see there's a nice sort of linear correlation, linear-ish, between this metric I defined and how late they get to the restaurant. Now, just to, you're not concerned, the delay gets higher there, but we do also predict this delay, and we tell restaurants how late the rider is expected to be to make sure that the food is prepared at the right time and customers still get hot food. It doesn't just sit there for this time. And on the right-hand side, we have quite a similar metric in some ways, the order duration. So the amount of time it takes from a customer placing an order until they receive it. And again, we have this nice sort of linear-ish correlation. And so this is now a nice grounding of a metric we can use to try and decide how many restaurants we show. And Wing-Lon is going to tell you about how we decide which restaurants to show. No.
Hello, good evening. So, if I were to summarize, Ben has so far explained to us what load actually means, and we can see from these charts that if load is high, then delay would also increase, and it also takes longer for the order to be delivered. And what I would like to cover now is how we actually manage load. Okay, so far is what is load, how to measure load, and now the second part of this talk is about how we want to manage load. So, what we see here is a map. Okay, color is not as expected, but so imagine we have a customer you see in the center, and this customer wants to order food. Under normal circumstances, we would show basically all the restaurants where we can deliver food from within a reasonable amount of time, and that is true as long as we have the right amount of riders. Okay, so if we have enough riders, we can actually deliver from wherever the customer wishes from. But as Ben already said, but there are sometimes unexpected events such as rain. And if it rains, then not all riders will turn up. And what we have is then a situation where load increases. So we get busy because a lower number of riders have turned up, and presumably they will have to deliver the same number of orders if everyone gets hungry. And this, of course, causes a problem to the network. So how can we solve this? So if we only look at the restaurants, okay, where we think we can deliver food from within a reasonable amount of time, given now the shortage in supply, then we would tend to pick the restaurants, the darker one burger symbols that are closer to the customer, because therefore, if we choose only to show those restaurants to the customer, then we can see that the travel time, or the time that it takes from the restaurant to travel from the restaurant to the customer, is shorter. Therefore, we would use less of the resources we have the fleet. So we can manage load by reducing the delivery area. So whereas before, if we had a sufficient number of riders, we would allow to travel longer distances, allowing the customer to order from restaurants which are further away. Now we are saying, if we do not have enough riders, if the load in the network is too high, we would then say, okay, then show smaller number of restaurants, and preferably those that are closer to the customer, such that travel distances are shorter, making sure that the network during high load is more efficient. Because if we already have a lower number of riders, we don't want to additionally ask them to travel for longer distances. The question then arises, so how should we then set this optimal radius? Okay, so how can we possibly do that? There are two extremes. Okay, so one would be to say, well, just show the customer one restaurant, which is the closest. Okay, this would surely make sure that the network will recover faster, because the rider has to travel very, very short distances. Of course, that's not optimal for us, because if I were to show every customer just one restaurant, the chances that he or she will order from this one restaurant is not very high. So in that case, we may have recovered the network, but at the cost of actually not getting any orders, and that's actually, of course, not ideal. So if we want to have more orders, what should we do? Well, we could possibly offer everything, okay? Even distances that we further have not considered. That would surely increase conversion, because we show the customer much more restaurants, and which would also increases the chances that the customer would order from. But of course, that goes against our original goal as to making the zone more efficient, as to managing the load in the network efficiently. So these are the two extremes, okay? Either making very, very short distances, showing only the closest restaurants, or allowing the customer to order from almost everywhere, showing very, very long travel distances. And somewhere in the middle should be a nice niche area where we are aiming for. So we have an algorithm that's trying to figure this out for us. And in this particular case, we use a regularized logistic regression. What we can see here is that on the x-axis, we have the delivery network load, the feature that Ben explained to us. This is one of the input features. And what we want to do with it is we want to predict as to how high the load will be in X minutes. Okay, so I phrase it a bit shorter as to what is the probability that we will be busy in X minutes. Okay, so the higher the load is, the higher the probability is that we will be busy in X minutes, and the lower the load is, the lower is the probability that we will be busy. And that red vertical line is the maximum network load that we are able, or that we're happy to endure to serve customers under, because we know that if we deliver order up to that network load, the service levels are still within the agreement. But if we go any beyond, then you can see from one of Ben's previous slide that if network load is just slightly bit higher, all of a sudden we wouldn't show any restaurants. and customer can't order from anything. So that is then a scenario which, of course, we want to avoid. So we have a regularized logistic regression, and network load is just one of the features that we put into this model. There are, of course, also other features, such as the time that it takes for the rider to travel from the restaurant to the customer, the actual delivery area that the customer and the rider are in, time of day, okay, because there are peak times, such as lunch and dinner, where we experience different levels of busyness, and day of week, okay, so weekends are not different to weekdays, and a variety of combination and interactions effects of these and other features. So again, well, the pointer is not working. So there are two extremes that we want to avoid. So we do not wish to be in an area where we really have low, very, very low load, such that just offering one restaurant. And the other extreme would be that we do not want to go to the other extent that we actually offer everything, so that we end up with a very high load state. So how are we going to do this if we have such a model? How are we going to use this to manage load? So as we do with any other trained model, we first train the model and then use it to predict. So in this graph, I just show one of the features, which is restaurant to customer time. So having trained this model, we would be able to predict, if we just feed in the features, as to say, okay, if the feature is this, how likely is it that we will end up in a busy state? Once you have used this model to predict it, we can also use the same trained model and invert it, such as to say, okay, now if that's the case, if I am likely to end up in a busy state with a probability of X, what could I possibly do to end up in a non-busy state? Okay, so which means that here, I wish to leave a busy state, I wish to enter a non-busy state. What is the corresponding feature that I should actually aiming for, such that I can leave the current busy state and enter a non-busy state? So we have trained a model, inverted, and from this inverted model, we can then read out the feature that would allow us to get the desired result, and then use this feature to set the maximum travel time we are looking for. So this can work like this. This is just an illustration, okay? So what we see here is the number of riders on 2 consecutive Saturday afternoons. The blue one is the number of riders on a rainy day, and the orange or yellowish one is the number of riders on a sunny day. And we can see here, on rainy days, less riders show up. What happens to the load? Well, following the discussion we had from before, when it's sunny, then network load is lower than when it's rainy, because if we have less riders on rainy days, we are getting more busy. If we are more busy, the network load will increase. Okay, so far so good. Now, let's focus only on the rainy days, because those are the days where load management algorithm will become most active. Again, what you see here, the red dotted line was that line that we are happy to serve orders. If the load in the network exceeds this particular threshold, we would then decide not to show any more restaurants to the customer, such that the delivery network can recover. So how does it work now? So let's combine this with what we have discussed before. Okay, so our goal was to figure out how many restaurants, or actually which restaurants, we want to show to the customer. Okay, so the customer in the middle, those are the burger restaurants in the area that the customer could have ordered from. And how using the model, the logistic model, and inverting it will allow us to derive a particular number of the restaurant to customer time. And it works as follows. So when we have a high number of riders, then we have, of course, a low load because we are not so busy. If we are not so busy, then we said before, we would be very happy to show a selection of restaurants where the rider could travel very far away from the customer because we have the work fleet, we have the capacity to do so. Okay? Ordering food, allowing the customer to order food from further away restaurant does not cause any harm to the network if we have the right number of riders in the network. However, if we enter a state where the number of riders drops, and as a consequence of this, the network load increases, then we have said, then we need to shrink the zone such that the customer can no longer order from restaurants that are further away. And that's how the algorithm works. So it uses a trained model, and in every cycle, it keeps continuously predicting in real time as to how should I set the optimal radius, if you so wish, of the delivery area for such that the customer can always see the optimal number of restaurants such that the ideal load doesn't go any beyond the threshold. We should be clear that it's not our goal to kill load, okay? There needs to be some load. So we are not aiming for a scenario where we have 0 orders, okay? Because that's where load is lowest, but that's not what we're aiming for. So in a way, you can see this as an optimization algorithm where we wish to increase or maximize the number of orders during high load. And the last chart is where you see in the blue solid line the average number of restaurants that customer can see in that particular delivery area. And the green dashed line is the maximum number of restaurants that are in that particular delivery area. So meaning, when load becomes high, we have to manage it such that we can no longer show everyone all possible restaurants. We have to show them less restaurants, ideally those which are closer to the customer, in order to make the network more efficient. Of course, this is just a temporary measure, and once load recovers, then of course we are very happy to show again all available restaurants to the customer. So this is just one illustration, one example from one Saturday afternoon, and then you might want to ask, does it always work? So all algorithms that we design and test out in Deliveroo always have to go through an experimentation framework. And this algorithm was just tested a month ago with the following results. So TESS is the new algorithm where we exactly do this dynamic load management, where we always dynamically calculate the optimal restaurant to customer travel time to make sure load is optimized. And what we can see here is the new algorithm manages to avoid accepting orders when the delivery network is already suffering from extreme high load. Okay? Meaning, if we are already busy, we shouldn't additionally accept more orders. But it is not that the new algorithm is always closing the door and pushing customers away. The algorithm is also intelligent enough to say, when we are not busy, however, we should show more restaurants to the customer. And we can see in this light green area that we do get more orders when we are not busy. Okay? And as a result of this, this has shown the following improvements in the network, such as when the network is extremely under pressure and we have high network load, the new algorithm manages to decrease the delivery time by shrinking the zone. And at the same time, we can also shorten the delay that customers are experiencing. While on the other hand side, although we do accept more orders when we're not busy, we are not increasing those measures. So this is one example of the algorithms that we do here at Deliveroo. Other colleagues and other teams working on other data science projects, such as recommender systems and personalization. So when you go to our web pages, you are always greeted with a very delicious selection of food, but depending on your profile, the list and the order of restaurants that you see will differ. We're also working on projects on forecasting and scheduling optimization, meaning here the task is to forecast what the order volume in future will be, such that we provide the right amount of riders and schedule the supply in advance. Okay, allowing riders to book particular slots in particular areas, such that we can measure the expected order volume with supply. We also work on dynamic pricing, meaning we want to always calculate the optimal price we can show to riders, such that they are most likely to accept the order. So not every order is equal. Okay, sometimes riders prefer orders that have a short distance, or sometimes it is a restaurant that they wish or do not wish to go to, or it's the area, time of day of week. So there are a variety of features that go into different algorithms and models in this area. But this is just one of the projects in the dynamic pricing that my colleagues are working on, just to also show you a small selection of the other data science projects that we're working on. So I hope you enjoyed the talk.